Hey, sixth grade, here are your review notes for the folds, faults, and earthquakes quiz coming up. Here's some essential questions that I won't go over right now, but these are the ones that get us sort of started here to get your mind thinking about it. So moving forward, there are a couple different factors that determine whether a rock will fold or whether it will fault, crack. The first factor is pressure. A rock will if a rock feels more pressure, being pushed a whole lot, it will fault. It'll more likely break. If it's less pressure, it tends to fold. All right. So the first one is pressure. Second is temperature. Rocks that tend to be warmer, kind of like gooey caramel, they tend to fold. But if they're cold, they become more likely to fault. Kind of like a cold piece of caramel that you just got outside, it can crack. But if it's warmer, it can become more gooey. Rocks can kind of get sort of gooey. They can fold. So temperature is a factor. And the third factor is the type of rock. Some rocks, just depending on the minerals that make up the rocks, are more brittle. They break more easily. They most likely fault. Granite is an example of a rock that tends to crack, fault a little bit more easily than other rocks like sandstone that are more flexible. So it depends on the pressure, the temperature, and the rock type. Those things determine whether a rock will fold or fault. Now, folds themselves can cause hills and valleys. We've seen this picture of folding rock. We've actually seen this picture of faults too, but we'll come back to that a little bit later on. And there are basically three kinds of folds that you need to be concerned with. The first is when rocks fold up, they create an anticline. An anticline, you can remember with this A, an anticline is when they fold up. Or they can fold down, they sink down. Those are called a syncline. Or they can, most commonly, it's a combination of both, that you have some places where they're going up and down. So if you imagine all these places where you have sedimentary layers of rock, they feel a pressure, they can fold in these ways. Don't worry so much about a monocline. That's just sort of where it goes off on the side there. But mostly what you really need to pay attention with the anticline, syncline, and the combination of both. Those are the way that rocks fold. There was your review note page, so look over that. In this example, what do folds look like out in nature? And a lot of times the top part has been eroded. And when you look at the rocks on the surface, you get to figure out, you can kind of sort of interpret the folds you're walking across. Here are folds that have been weathered away, but you can see how within here, this yellow rock has folded underneath and comes back and reaches the surface back over here. This is a cross-section view. This rock that we say represented by the green color is folded underneath and it pops up too. And here's another example of that. Depending on how rocks fold, what you experience on the surface can give you clues into how the rocks are folded underneath. And this is important for geologists because sometimes these anticline folds can trap oil and gas. So if you can go on the surface and realize you're on top of a anticline, and you realize that that anticline, the types of rocks of that anticline could perhaps trap oil and gas, well, that's a good place to start digging a well to see if you can get that oil and gas. Those are fossil fuels that people use, that we all use as a form of energy to energize our lives. Here's another monocline. Don't worry so much about this page. But here's a syncline where the rocks have sinked underneath. They're folding in this manner. And again, you can kind of see, depending on how the rocks are slanted, you can see a syncline. There's another picture of a syncline that actually is the reverse of a fold. Or I'm sorry, the reverse of the hill itself, which is kind of neat. This picture shows you how the rocks were folded, and then this river kind of cut through the different parts there. All right, now faults. Faults are where rocks crack, a fracture, a break, is known as a fault. Here are the three types of faults. The three types of faults are created by three different types of forces, and those types of forces happen mostly at the three different types of plate boundaries. So the first type, the strike-slip fault, that's made by a shearing force. And with a shearing force, it pushes one side away from the other. So if we're looking down, say, on a road, and there's a fault right here, and it feels a shearing force, one side would go one direction, one side would go the other direction. A normal fault is caused by a pulling apart force, a tensional force. Now this is a side view. So there's Jane, and this is the rocks underneath. These rocks are pulled apart. One of them slides down, and where that slide creates an obtuse angle. This is called, again, a normal fault. This obtuse angle is important to remember. As compared to a reverse fault, that's come from a compressional, a pushing together force. If these rocks feel a compression pushing force, then one rock will be pushed up and over the other. This creates an acute angle. And this is important because NORA can remind you if it's a normal or a reverse fault. An obtuse angle is a normal fault, so normal obtuse. A reverse fault is an acute angle, reverse acute, N-O-R-A. So Nora can help you on this quiz to remember these two different types of faults. Okay, here's another picture of a whole bunch of normal faults where the Earth is being pulled apart. This page sums it all up. What type of plate boundary creates what kind of movement, right? And depending on the force that that movement creates, a compression, a tension, or a shearing force, you can either get a reverse, a normal, or a strike-slip fault. So this is an important page to look over. It ties together the fault types, the forces that cause those, and the boundaries where you find those types of forces. And again, down there's a little bit more of Nora. Again, this was a practice page. We practiced drawing there. Marshmallow challenge. Don't worry about that. Now to earthquakes. So earthquakes happen when along a fault there's movement, and that movement releases a whole bunch of energy. And that energy moves from one point away. Like ripples in a pond, if you dropped a pebble in a pond, the energy from when that rock hit the water moves away from that single point and moves out. And as things go far away, the energy dissipates. It kind of gets less and less. So if there was a duck near where the pebble fell in, it would feel more energy. A frog that was farther away from it would feel less energy. And the same is true for earthquakes. The closer you are to an epicenter of an earthquake, the stronger the earthquake will feel. The farther away you are, the less energy you will feel. Now, the waves that move from an earthquake, there are three different types. The first are primary wave, prime being first. Primary waves move back and forth like this, and they are fast. They move first. Then come the secondary waves. They go up and down, and they're slower. And this difference between the P and the S wave speed is very important, as we'll see later on. The third type is right close to the epicenter. Before those two really get to be pulled apart, when they're still pretty close together, the combination of those two together creates surface waves. Now, these are the most damaging because they're right near where the epicenter is, and they can cause damage on the surface of the Earth. Now, where the actual earthquake starts along the fault is known as the focus. And the place on the surface of the Earth, right above the focus, is called the epicenter. So we put on a map, here's the epicenter. The earthquake, that's where it starts, at least on the surface, but truly where the earthquake really originated was below that, deep in the Earth along the fault. And you can see from here, if this is the surface place of where the fault reaches the surface, there's kind of a cliff there for this obtuse angle, normal fault. But the actual epicenter is farther away from the fault, even though the earthquake occurred on the fault, because it actually occurred a little bit deeper down in the Earth there. So make sure you know the difference between the epicenter and the focus. All right? And you can see from there all the rays of energy, the moving waves moving out from where it occurs. Some terminology: seismologists, seismometer. Think of the seismometer as the machine that makes a seismograph. I know sometimes these words are used interchangeably. The seismograph can show you the magnitude, the strength of an earthquake. That magnitude tells you the strength is a number, and the Richter scale is a way to kind of compare the relative strengths. And remember that they're not straight linear progression of their strengths. It's actually 32 times every time bigger. You don't need to memorize that directly. Just know that when you get earthquakes that have magnitudes of 7, 8, or 9, they are immensely bigger than ones that are 1, 2, and 3. They're not just 3 times bigger. They can be thousands and tens and thousands of times bigger than, in terms of energy, than the earlier ones. So keep that in mind. Last couple things. Oh, this was just a picture, remember, of the person when I was in college, and we had the seismometer down here to measure the earthquakes from when they were building the new science library, and they'd have explosions go, and our seismometer in our geology building could sense the energy from those explosions, and it would send it up to a seismograph that would go, and we would see that energy displayed on the graph when the seismometer would feel the energy from the explosion over there. Earthquake safety, these are good. We went over those. Lots of good things to know. We've been doing our earthquake drills, so that's important to know. Big idea questions here. Can you predict where earthquakes can occur? Yes, near plate boundaries and near faults. If you're near these things, that's where earthquakes occur, but exactly when, that's trickier. You can still be prepared, but you can't be prepared in the sense of, oh, an earthquake's going to happen tomorrow, let's get ready. You're not sure exactly when it's going to occur. Now, this is important. We talked about how if different cities know how far away an earthquake occurred. By sharing their information with each other, they can find the epicenter. And in this example, we said, well, if San Francisco figures out that the epicenter happened about 25 miles away, they draw a circle there, and Stockton said, oh, we felt the earthquake was 50 miles away, and it created a circle around Stockton that's 50 miles. There are only two places where the 25-mile circle and the 50-mile radius circle intersect, here and here. And to get of those two to figure out that last point, you talk to one other city, and if they're like, oh, it's 150 miles, say, they draw in a 150-mile circle, and where the Sacramento circle and the Stockton circle and the San Francisco circle, where they all meet, must be the location of the epicenter. And that's a way to find out where the epicenter is. In this case, it looks like it's along the Hayward Fault near San Francisco. Whoops, I just moved it there. Okay. This page, don't worry as much, but this one you do. When we did the epicenter activity, this idea of understanding, back here, that P and S waves travel at a different speed. And that's important because if you know the difference between the arrival time of when a P wave reaches the city, here it comes, and then the arrival of the S wave, there the S wave comes, the more time there is between the arrival of the P wave and the arrival of the S wave, the farther away the earthquake epicenter is to that city. And this handy-dandy epicenter distance chart can show you that. If the time between the arrival of the P wave and the arrival of the S wave is, say, in this case, 2 minutes and 40 seconds, we can figure out that it's about 1,800 or 1,800 kilometers away from that city. If it was, say, I don't know, let's say like at 8, if it was 8 minutes, start at 8 minutes, you go over to where you hit the green line, fall down, a little over 6,000 kilometers away. So the more time there is between the arrival of the P wave and then the arrival of the S wave, the farther away the earthquake is. The less time, only a little bit of time, it's closer. If you're given those times, could you find the epicenter? Just like this one. If you're given times, could you find the epicenter? And you will need to do that on the quiz. We take those distances, just like we showed before. You can plot them on a map using a compass and figuring out, if I know 3 distances, epicenter distances, I can plot those and draw circles with those defined epicenter locations. And that's what we did in our classroom epicenter. That is it for the notes on this page. This last note just sort of shows you where, this is from your book, where earthquakes happen more often in the United States. They're more often near the edges of plates. There's some older faults in here that cause a little bit of concern. But over here are the big ones where there are active fault boundaries, active plate boundaries that cause earthquakes. With the exception of this one, Hawaii, look at this. A lot of earthquakes along this active volcano. And notice that the older islands get less and less earthquakes. They've settled down, so to speak. But that's it for this little quiz that you're coming up. There will be nothing on the tower. The tower is separate from that. In fact, we won't finish the tower until after winter break. But it's good to look over this for the upcoming quiz on folds, faults, and earthquakes. That's it. Check in with me if you have questions. Bye.